Hello, everyone. I'm Kane, Safeheron's partner and VP of Technology. Bybit suffered the largest crypto theft in history. The hackers stole about 1.5 billion worth of assets. I won't introduce the whole incident today, as our article has covered most details. Now, let us get to the point. I will showcase how Safeheron safeguards assets against such attacks. As Bybit used Safe Wallet, hackers chose to hack the developer's computer of Safe. They then can forge its UI, and they took advantage of Ledger's poor visibility of transaction details. These misled Bybit's financial team and CEO Ben into believing that this is a regular transaction. But actually, they signed a transaction to an altered smart contract address, a transaction to transfer the cold wallet control. To this point, the attack completed. Safeheron's underlying architecture is based on MPC and T-Tech. So the similar attack cannot directly happen in Safeheron's wallet servers. After Bybit's breach, our customers also asked us, if someone tries to attack Safeheron, is that they only need to attack whitelists to tamper the preset whitelisted addresses? When transfer funds, though the whitelist name remains the same, the actual address has been replaced. Then coming to the approval, approvers mistakenly believe that they are approving a legitimate transaction. However, the actual destination has been tampered. This will result in a similar outcome. A very good question and attacking method. Today, let's see if Safeheron can defend against such attack. We conduct this attack demo in the development environment along with other 5 colleagues. They are on standby in the online meeting. Throughout R&D and permission management, Safeheron strictly adheres to the principle of least privilege and separation of duty. So, we will need multiple parties together to strike this attack. To minimize the exposure of the attack surface, I won't introduce the specific position of each colleague at Safeheron. Now let me use a preset ETH address to add it as a whitelist. See how whitelisting and funds transfer work in Safeheron. Add a whitelist here. Enter name, type, address. Enter two-factor verification code. Now, you can see that the whitelisting request has been submitted. From the mobile app, you can see a new approval task for whitelisting. Please note the address and its name here. This address ends with 688A. Approve this request. Approval completed. Back to whitelist page. The whitelist is now valid. Now let's transfer funds. The destination here, choose a whitelist. Enter an amount. Now send. Two-factor verification is required. I've initiated a transaction. Now, on the mobile app, here is a new pending approval. Let's take a look. Sent funds from Wallet 1 to the whitelist. The transaction type is whitelist. This address ends with 688A. Now proceed with approval. MPC signing succeeded. The transaction succeeded too. The transaction is pending now. Let me explain the security mechanism for whitelists in Safeheron. We've designed a multi-layer defense model for whitelists, which are database signature, TE policy engine, decentralized verification, and what you see is what you sign. Later, I will explain each layer in details. First, let's check out 3 attack demos. These are also typical attacks on wallet service. From these 3 attacks, we can see if our multi-layer model can effectively defend funds. Messaging colleagues to strike the first attack. While conducting the attack, let's see how the first layer defend against risks. Whitelist data is stored in database through encryption. Signature key is stored in the encrypted middleware. Security team is responsible to it. R&D team cannot obtain this key. When backend uses whitelist data, it will check if the data signature is valid, run the business logic if it is legitimate, otherwise it will be blocked with an error message. So the first attack is to tamper the address in the database without changing its signature to demo when attackers obtain database permission. Let's see if the attack has completed. Okay, the attack conducted. Get back to whitelist page and transaction initiation. Refresh this page. A security check message popped up as the security verification failed. Let me try initiating a transaction. An error prompted when I try to choose a whitelist. Now continue with second attack. My colleagues are going to conduct the attack. The second attack is going to tamper the whitelisted address and its signature. For us, this is to act like when attackers obtain signature key. Let's wait for the attack to be completed. What we expect from this attack is that you can see the whitelist in the list, but your transaction will be blocked because of TE policy engine. The attack finished. Get back to whitelist page. From whitelist page, you can see the whitelist here, and it's valid too. However, its address has changed while its name stays the same. It's no longer an address ending with 688 and A. Let's initiate a transaction. Select a whitelist. Enter an amount and initiate. Enter two-factor verification code. You can see when initiating a transaction, there will be a security verification, and now it's failed. The behind reason for it is that our T policy engine blocked the transaction. Let colleagues to continue striking a third one. Meanwhile, let me explain how we blocked the attack. How our TE policy engine works? Actually, each approver has an authorization private key in their mobile apps. They will use this authorization private key to sign whitelist name, address, and other info. And each approver needs to sign. TE policy engine will collects and verifies those signature. If verified, TE will believe this is a valid whitelisted address. The approval process is also valid. TE policy engine will collects and verifies those signature to sign and store the data again. This also explains why the previous attack was blocked, though the address and signature were tampered. When initiating a transaction, TE policy engine will compare data with that stored in the local T. If verification failed, TE will block the transaction. The third attack has finished too. The third attack is to simulate a malicious T program to bypass processes such as data verification. This is when internal C levels have been attacked. As T is attacked, attackers obtain its control. Let's see how it goes. From the whitelist page, the address is a tampered one. It's normally displayed. Let's initiate a transaction. When initiating a transaction, no hinder from choosing a whitelist. This is already a malicious address. Proceed. Initiate a transaction. Enter an amount. Initiate it. Two-factor verification code. The transaction is successfully initiated. Now turn to the mobile app for approval. From the app, refresh the page. Now you can see a task pending approval. Its name is My Wallet, but the address is a tampered one. This is what you see is what you sign in Safeheron. Ensure that the on-chain transaction is the same as the current transaction shown in the approval. Let's try to approve this request. A signing error prompted. Actually, the security verification has failed before MPC signing. Now get back to this PowerPoint. The final step for transaction in Safeheron is to have every signer, including 2 cloud signers and customers app, receive complete transaction details and T report about the transaction. Each party then verifies all info once received. This is the decentralized verification. With MPC feature, we implement decentralized verification and approval. If attackers want to bypass this verification, they have to breach all the signers. We've also reduced risk exposure. Only mobile app and signer are risky points. Every party must complete a 3-step verification, which are what you see is what you sign. Safeheron app ensures that the transaction you see in the UI is the one that will be confirmed on the blockchain. Every signer performs a blockchain transaction serialization process. Locally compute the transaction hash to be signed by MPC. MPC threshold signing can proceed when all parties compute identical hashes. Vice versa. So even in the circumstance of the whitelist being tampered, the address in the UI is actually a malicious address. The second step is to verify T-report. T-report re-verifies the approval process, approver and its approval threshold, and transaction details. It ensures that the transaction is initiated through Safeheron and satisfies the preset approval process. Verify the validity of TE report to ensure transaction legitimacy. We implemented a malicious TE program to bypass protection for destination. So T-report has been verified successfully. Then, we come to the final step, the decentralized verification for whitelists. Approver's app stores the authorization public keys of all members. I've shared before, every approver for a whitelist approval will use their local authorization private key to sign the whitelisted address. So, when approving a transaction, if the destination is a whitelist, the approver locally uses other members' authorization public keys. The keys refer to the public keys of members who have approved this whitelist. Use those keys to verify the whitelist. We did attack the address, but we can never forge the signature made by the authorization private key to the address. Thus, we successfully blocked the attack by verifying the address signature. At last, there are a few points worth considering. In T, when verifying the whitelist signature signed by team members, how we ensure the trustworthiness of members' public keys. When transmitting public keys to TE, how we ensure the trusted transmission, and how we make sure the exchange between public keys remain trusted. How we eliminate man-in-the-middle attack. We will further explain these questions in our closed-door webinar. Let's make a conclusion. Throughout our implementation, the premise of product and security design is the zero trust on R&D, operation and maintenance, security, and all other internal teams. The trust roots in codes, machines, encryption chips, and customers themselves for system design and implementation. Therefore, Safeheron sets 2 core principles. First, for crucial sensitive data, high-level sensitive data and key execution logic and algorithms must be implemented by TE mechanism. This is why we utilize T-Tech to build Policy Engine and Sina. Second, for customers' key actions and authorization, decentralized verification is required to implement the decentralized authorization. This is the final stage of the mentioned multi-layer defense. These two principles complement to each other, guiding Safeheron to design and develop key systems like whitelisting MPC node. With this mindset, Safeheron offers a complete self-custody service against internal collusion, external attacks, and external hacking and malicious insiders on the customer end. Thanks for your watching today.